Hello everyone. In this lecture we're going to continue our theme of using uncertainties from machine learning models to do interesting science by exploring the notions around optimal experimental design. Before we get into that topic, let's talk about experimental design in general by going over a few of the kind of static experimental design methods that you might be familiar with. And these are all built around the idea on how can I design my experiments ahead of time such that they'll give me the most useful information, and include methods like fractional factorial design, which allows you to test different factors and be able to create a data set that is maximally rich for identifying what happens when I raise and lower different factors. There are also techniques like Latin hypercube sampling, where if given a finite budget of points, I pick ones that ensure they're maximally distant from each other and span over the entire range of a data set, or a range of possible values for that data set. For instance, this cartoon here shows how I can take 5 factors, divide my different variables into 5 levels, and pick each point such that there are no other points in the same row and column, and choose the value such that they're maximally spaced apart from each other. If you're not familiar with either of these two statistical techniques, you're definitely familiar with political polling, where a lot of thought is placed on how they can generate random samples of the population, either by sampling voting records in a way that should mimic the overall population, or by picking telephone numbers at random. And while these static methods for experimental design have their place, the area we're going to talk about in this lecture is how you could design an experiment such that you can leverage the ability to learn between experiments. And as we demonstrated in yesterday's lecture, there are many methods for machine learning that let you learn and also be able to identify the gaps in where your model's understanding is. And those techniques broadly fall under the category of optimal design, which are based on this conceptual loop, which is illustrated from a review paper from Turab Luqman, where you iterate a process of starting with some initial understanding to build a model. Keep in mind these could be those priors that we discussed that are important for Bayesian models. Using that model to identify which new points I should test, testing them using some kind of high fidelity calculation or an experiment, something that you don't want to do very often but gives you a lot of information, and then feed that back to update your understanding, and repeating this process to gradually identify the experiments that will allow you to perform computations or tests that give you the most information. Now, this overall concept is been used in many areas of science and consequently goes by many different names. You may be thinking that this sounds like a lot like active learning, which is the term used for this kind of iterative design process for the machine learning community. Also in mechanical engineering, they tend to use the terms surrogate-based optimization. You may also have heard of Bayesian optimization. And all of these really describe the same iterative process and are all composed of 3 major components. Some kind of machine learning model that can give you predictions about what the outcome of an experiment should be and tell you what the uncertainty of that prediction is. Some kind of space of points you want to search over in an optimized manner. And finally, some policy for determining how you should perform that sampling. And I've bolded that point because that policy is what really distinguishes different kinds of active learning or optimal experimental design approaches from each other. Now, to introduce that concept, let's consider two potential ends of a pole on how you can choose which experiment to perform next. So imagine that you've got a series of experiments that you can perform in some feature space that are distinguished not just by the predicted value of your model, which is this red line, but also the amount of uncertainty you have in that model's predictions. Now, one way you could go about selecting these points is to pick the experiments which have the greatest uncertainty. In this way, you gather the data that explores across your region of potential experiments very effectively. Additionally, you could state the goal is, I want to evaluate the experiments that give me the highest value of some property. And there you could devise a policy where I disregard uncertainty altogether and I pick the point that has the highest mean or the highest likely value predicted based on my model. And I could say this is exploiting my model's predictions. And often you hear these two different poles described as differences between exploration and exploitation of the experimental space. Now, with this concept in mind of you could have different policies for how you want to choose your experiments given information from your model, there are many shades of gray in between. And if we look at just one class of algorithm, Bayesian optimization, which use models like this Gaussian process described here, which give you means and standard deviations for each of your predictions. You can imagine a few different ways of combining those two bits of information to help you identify what point has the most value. Now, this process of taking information about a point and assigning it value as an experimental option is called an acquisition function. And in this example here, you can see how that varies value according to not just the mean value of the prediction or the uncertainty, but some complex combination of the two. And there are really a plethora of options of acquisition functions that you can use that each have different properties. Now, we've already talked about uncertainty sampling, where I assign my value based on the uncertainty I have in my prediction. You can imagine here I'm showing for a given prediction as a probability distribution of its outcome, where I have both a mean value and some distribution of possible outcomes. So besides looking at just the width of this distribution, I can also look at its mean, and that's greedy selection. But there are a few other places that interpolate between them, like upper confidence bound, where I define a trade-off parameter beta, which controls how much I favor a high mean for my predictions, weighed offset by my uncertainty in that prediction. And there are also more sophisticated measures like the probability of improvement, where I can take the fact that this is a probability distribution and say compute the likelihood that my predicted value x is going to be less than some threshold x prime. So this shows you four common methods for defining an acquisition function. And if this is something that you want a deeper math on, or some examples on how these can be derived from statistical principles, I recommend reading this lecture from Roman Garnett at Washington University that goes into that mathematical side in a bit more detail. But these really only scratch the surface of potential options you can use for acquisition functions. And it can get very complicated depending on what distinguishes the types of experiments that you run or the type of model that you have that kind of complicate whether each of these acquisition functions would be a good choice or not, or stated more optimistically, provide some opportunities for finding an algorithm that's well suited towards the particular experimental design challenge you're facing. And just to give you some examples of what these kind of variables might be, these could be whether you're performing your experiments one by one, or at each step you select a batch of experiments, and there's a whole field of batch active learning approaches that help you select a set of experiments that are, say, both valuable by themselves and sufficiently diverse from each other that if you explore them all at once, you're going to get not just good information, but a kind of a rich diversity of information that will help you improve your model. You can also exploit the properties of different learning algorithms, such as looking at linear regression and knowing how that's fit. You can pick a point based on how much effect it's going to have on the actual linear model. There are also multi-objective techniques. There are ones that are based on experimental designs, where you can use multiple different types of information to improve your model. And really, this is to go on to say that there's a whole field of people who really specialize in being able to understand how experiments are performed and develop mathematical approaches for designing experiments in an optimized way. So really my advice here is to make a friend who's an applied mathematician, particularly one that studies in this area of optimal experimental design, and through that you can really find the best approach for being able to use optimal design in your own work. Now, with all that theory aside on explaining what are the components of these types of learning algorithms, we're going to go into a little bit more detail now to show how they can be used in the context of materials engineering. And we'll start off this by breaking out a paper that kind of really spurred a lot of the advancements we've seen in the materials community, which is work from Jouet et al. From Los Alamos National Laboratory about 5 years ago. What they did is they used experimental design techniques to optimize the composition of shape memory alloys such that this property called the hysteresis is minimal. Now, this hysteresis defines how different the temperatures when I cool down a material and it will reform into its original shape, or when I heat it up and I can train it into a new geometry. And if you simplify and if you get these close together, I believe that gives you good properties for like energy damping applications. Now, material science aside, we can take a look at their study, which they used to optimize the composition of these alloys and break it out into those three components that we discussed earlier. They used a support vector machine regression model where they got uncertainties by training a whole ensemble of these models via a technique called bootstrapping, where you train each model on a different set of data, and looking at the distribution of predictions from each of those models within that ensemble to give a notion of certainty for each of the individual predictions. Now, given that model with uncertainty, they evaluated over a search space of many different alloy compositions and used a technique known as knowledge gradient to identify which batch of experiments they should perform in each round. And using this as an iterative process to guide their experiments, they quickly found an alloy with a hysteresis about half the size of what they started with, using only a few dozen experiments. And this result here is still remarkable and went on to spur a lot of effort, in especially the materials community, on figuring out other ways we can use these design techniques. One that's relatively recent and from Argonne National Laboratory is using Bayesian optimization to tune the parameters of an industrial process to have a better outcome, or to have better materials coming out of it. And for this one, they were trying to optimize a technique called flame spray pyrolysis, using a technique based on Gaussian processes, which, as we learned a few lectures ago, are based on a kernel. And the Gaussian process is a version of that that applies uncertainties to each of those coefficients you learned for your kernel method, allowing you to be able to give predictions of the or to give uncertainties on your outcome. They use this Bayesian optimization to search over a space of potential processing parameters that are within the limits of their machine, and use a technique known as expected improvement to pick which parameters to run next. And you can see here they were able to effectively improve the materials coming out of it. I'll also note, just as an aside, As you can see here where they combined the static experimental design we talked about at the very beginning of the lecture, particularly the Latin hypercube sampling, to pick experiments in a limited number that gave them enough data to really train an efficient model from the beginning, which allowed them to kind of find their optimal parameters with only a few experiments. You can note they only did 16 here, and by the 17th, in the view of the authors, they had really run out of good samples to test, so their Bayesian optimization algorithm was telling them to go off and try something completely random to see if that could give some chance of improving the model. Incidentally, it was their worst test of the lot. So given these two in-depth examples of where Bayesian methods have been used, we're now going to go through and kind of show some examples of really where people have started to do some very sophisticated things. The one I'd like to start with is from a team from NIST and a few of the other national laboratories and universities that has a very clever method for identifying how to perform or to optimally pick experiments for optimizing materials by considering not just how properties vary within a particular region of materials, but also exploiting the fact that properties discontinuously change when you switch between phase boundaries. And for those of you not from a materials background, these phase boundaries define where a material structure changes discontinuously as a function of composition. So you can get some very different structures in the material, which give it very different properties. And by exploiting that knowledge, they designed an experimental technique that lets them quickly find optimal materials within a large space of possible options. There are also a number of studies that have identified how we can take conventional atom scale optimization problems like finding how a molecule bonds to a surface, or finding how a surface forms a so-called reconstruction, where the atoms rearrange themselves to a low energy configuration on the surface, using these Bayesian optimization techniques, and leading to success of being able to find those optimized structures much faster than kind of conventional optimization techniques. There's also a wealth of information from the force field fitting community, where they could find that by intelligently selecting what materials they want to include in a training set for a model, they can get a model with much better performance as a force field that is predicting the energy or forces acting on an atom with much greater fidelity, with in some cases a small fraction of the training data from previously. And there are also neat ideas that come from the atom scale or the force field fitting community, like partitioning your potential experiments into clusters first, such that you can force your optimization technique to pick from very different groups of data in order to make sure that it's really selecting a good diversity of training points. And this is actually work that came out of one of my colleagues at Argonne, Ganesh Sivaraman, just a few months ago. And kind of bypassing these more objective-driven searches, like trying to find a best material or trying to find a model with the best performance, there are even ways you can use active learning to go out and apply curiosity to discover things. And this is work done by a group in Scotland, I believe, where they constructed a robot system that will autonomously explore different mixtures of different oils at different temperatures to see what kind of droplet formation you can find. And by defining a curiosity algorithm where this model or this autonomous system would come up with what it wants to explore, they found that it could come up with many different behaviors of these droplet systems kind of on its own accord. All they could do is task it with, I want to find how many different things you can discover, and this curiosity-based system could go off and do it for them. And that mentioning that this system is autonomous, it's a robot that chooses its own experiment, analyzes the data, and performs them. That really brings me to my last point of things to consider with optimal experimental design, which is well captured by a recent review from George Crabtree, really illustrating that with these optimal experimental design algorithms, when you combine them with robotics, you can really take humans out of a lot of the scientific process and be able to create these self-driving laboratories where it's the role of a human scientist to identify what the laboratory should be doing and really allowing mathematics and robotics to take over actually performing the scientific studies. And this wraps up my lecture for the day. And the two things that I want you guys to walk away with are that the ideas that optimal experimental design are many different algorithms for being able to learn what experiments you should do next while actually performing those experiments. And there is an enormous field of algorithms to do those that roughly split the poles between algorithms that have goals to explore potential space of experiments most efficiently are those that are goal-driven in trying to exploit what you already know to quickly find, say, experiments that will give you a desired result. Towards the end of the lecture, we covered many different ways that these active learning methods have been used so far, and it illustrated in a few cases how they're indeed broken up into simple components of a model that tells you it's the uncertainties and its predictions, and a policy that lets you search over a space of potential experiments. And really the thought I want to leave you with is that these algorithms really open the door to having laboratories that are purely autonomous. And this is very well realized within the materials and chemistry community, who have already started to build robots like the one you're seeing here that can really perform quite complicated experiments, and people are growing the experimental design algorithms to really keep up with these kind of robotic systems that are available.